Hello, everyone, and welcome to Echo Live. My name is Anna, and I'm coming to you from the Michigan Science Center's Echo Distance Learning Program. Today, we'll be talking all about light, and in honor of National Wear Your Pajamas to Work Day, I've decided to show off some of my favorite pajamas for you. If you're not already wearing your pajamas, today is your free pass to do so. I know some of us are lucky enough to get to wear our pajamas to work every day if you're working from home. But even if you're working on your science homework, working from home, today is your day to wear your pajamas and feel no shame about it whatsoever. If you do choose to wear your pajamas to work today, take a picture and send it to the Michigan Science Center on Facebook or on Instagram. We'd like to see your get-ups in honor of National Wear Your Pajamas to Work Day. So today we're talking about light, and most specifically, we're talking about visible light. So we've covered light a little bit on Echo Live already when we talked about our microwave it segment. We said that microwaves are a form of light that we find on our electromagnetic spectrum. So all forms of light we find here on the electromagnetic spectrum. We talked about microwaves, which are right over here. But today we'll be talking only about visible light. So light that we can actually see with our human eye. So visible light, if we take a look at just that part of the light spectrum, we say that visible light for humans falls between 400 and 700 nanometers. So only these size waves, so these are measured in nanometers. So there's 1 billion nanometers in a meter. Only this wavelength of light can be observed by the human eye. But not all eyes are the same. So visible light is not the same for all living creatures. Most humans can see between 400 and 700 nanometers, depending on certain types of color blindness. Some people are missing parts of this visible light spectrum. As we age, sometimes our visible light spectrum narrows a little bit as well, but other living things observe visible light differently. So if we take a look at this slide shows the visible light spectrum for dogs. So here's an image that humans might see. So we can see lots of bright colors, good definition, but on the right, this is what a dog might see looking at that same spot. So this is a simulation of the receptors in dog eyes. Down below, we see the visible spectrum for dogs. So you can see that they're really missing that red part of the visible light spectrum, even orange, and they're also missing the purple end of the spectrum. So they're really limited to this kind of yellow to blue range of visible light. So similar to humans, but definitely a much smaller part of the scale. Dogs don't rely on color vision so much as humans do, but they have other senses that make up for that, like a really heightened sense of smell. But other living creatures also have different visible light spectrums. So this is the visible light spectrum for a bee. Similar to most insects, they don't see red color very well. So here's a human visible light spectrum. We can see all the way from red down to violet or purple, but bees lack a lot of that red color vision, but instead they make up for that by seeing well below that 400 nanometer visible light. So they can even see into the UV light spectrum. That helps bees to know where pollen might be located. So this is what humans might see, and then this is a simulation of what bees might see. They actually see UV light. But we're talking about visible light for humans here, and so we're going to talk about how we can actually produce light. So we've got a few different demonstrations all about light bulbs, how we create light using mechanical or electrical energy. So we've got a few examples here. We've talked about this a little bit already when we talked about plasma. So plasma we most often observe as lightning naturally occurring here on Earth, but we also have devices such as this plasma globe here. And we also saw this with our vacuum jar. We turned that into a plasma globe as well, right? So this is powered by electricity. We can turn electricity into visible light by just ionizing certain types of gases. Right, so most of the gas inside this plasma globe is krypton. And krypton, when it's ionized and turned into plasma, gives off this very purpley, almost pink kind of color. but not all gases, when they're ionized, emit the same spectrum of visible light. And we're going to take a closer look at different wavelengths of light produced by different gases using this device right here. Now, this is basically just a housing that we can put different tubes of gases inside of and take a look at what colors we see emitted by those specific gases. So krypton was one of those gases that we find on the periodic table, and we saw from our plasma globe that that burns a bright purple. But let's take a look at some other elements. Let's first look at hydrogen, which is element number 1 on our periodic table. We talked about how hydrogen makes up almost 90% of our sun. So we might know what hydrogen looks like. We'll go ahead and we'll turn on the power, which is going to send electricity through that glass bulb, which is vacuum sealed with only hydrogen gas inside. And let's take a look at what color that gas ionizes to. All right, so we see a pretty interesting color change here. We see that this gas burns kind of a bright purple color, at least to our visible eye. But what's interesting about these spectrum tubes is even though we observe this kind of bluish purple color, this is really the final product of a few different wavelengths of light. Almost like painting, we can mix light together. So if you mixed red and blue, right, in painting, you might get purple. So this is not strictly purple light. I can show you that by using this diffraction grating. If I hold it up in front of the glass, this diffraction grating actually breaks up that light into its individual wavelengths being emitted by that gas. So we can see that the final product is this bluish purple, but really this tube is emitting red, orange, blue, those wavelengths of light as well. But our eyes see this as our final product. All right, let's put another gas in here, and maybe you want to take a guess at what color this gas might glow. All right, our next one is helium. So we did hydrogen, element number 1. Let's do helium next, element number 2. If you have a guess about what color our helium will ionize to, go ahead and type it in the chat. So we've said that all of these gases will appear different when they're ionized based on the amount of energy they emit. When they're ionized, the energy picks up and then drops back down and photons are emitted. They travel at different wavelengths, which give us those different frequencies of light, which we saw in our visible light spectrum. Let's see, any guesses for our helium tube? Element number 2. I see some guesses for orange, white, blue, red. Ooh, lots of good guesses here. I see some guesses on Facebook. Go ahead and type those in the chat if you have any final guesses. Let's go ahead and turn it on in 3, 2, 1. Ooh, so this one kind of gives us an interesting combination of colors. Right where the gas is ionizing near the electrode, we see kind of a whitish light. But towards the center, right, we see kind of a yellow glow. Let's hold up our diffraction grating and see what kind of wavelengths we're really looking at here. So we see that kind of peachy yellow color as our final product, but you can see using our diffraction grating that we have red, yellow, and blue light being emitted from this helium tube while those gases are being ionized. All right, let's try another one. The next one we'll try is mercury. So you might know what mercury looks like if you've ever seen a thermometer. Most thermometers have liquid mercury in it, but go ahead and tell me in the chat, what color do you think ionized or plasma, when we look at mercury, what color do you think we might observe here? Go ahead and tell me in the chat. Again, this one is mercury. We most often find it in thermometers in its liquid form. I see some guesses starting to come in. I see a guess for red. I see a guess for white, yellow. Michelle tells me gray, red or orange, red, red, red. All right, let's take a look. Oop, let me turn off my virtual background here because I don't want anyone to be deceived by the glow near the electrons. But this really glows a very, very bright blue. Maybe not what we expected, right? So in its liquid form, it's definitely a dark red color. We can see that inside thermometers, but when it is ionized and put into its plasma form, it glows a beautiful bright blue. Let's take a look really quick at our spectrum or our diffraction grating. And you can see that this time we don't have a whole lot of those red wavelengths of light. We actually don't see any through our diffraction grating. We see kind of a bright green and a blue wavelengths of light. So many less frequencies, individual frequencies of light go into contributing to this bright blue color. Now let's try one more gas with our spectrum tube here. Just one more. This one is neon. So if you've heard of neon signs, right, they all rely on this principle, although they're not all necessarily full of neon gas. So neon signs work exactly like this spectrum tube, right? We have glass tubes that are vacuum sealed, meaning that we pull all of the air out of them except for the gas that we're trying to ionize. So we pull all the air out initially. We then fill it with a gaseous form of the element based on which color we're trying to get. Focus down here on our spectrum tube. All right, so this one is neon. This one is neon. Go ahead and tell me. Kate says purple. A couple people tell me blue, green, or aqua. Ooh, green's not one we've seen so far, really. I see a couple people in Zoom telling me yellow. All right, let's take a look. And there is that very, very bright red or orange color that we've been guessing for so far. So neon makes this very, very bright, very orange color. Even if we look at it through this diffraction grating, that really is almost the only wavelength being emitted by this gas. So we don't see a lot of blue, we don't see any green. We're really stuck here in this kind of orange to red spectrum of light. This makes for great neon signs. Neon gas was the original one they used in those neon signs, which is how they got their name. But now we fill them with different gases in order to produce different colors. So pretty interesting stuff. Let me turn my virtual background back on here. And then we'll turn off our spectrum tube and we'll move on to the next part of our demonstration here. So how does this tie to the light bulbs we have in our house right now? We don't normally use neon light bulbs inside our houses. We're really looking for that white light in order to power up our homes, right? But light bulbs took a really, really long time to be invented. It was a very difficult process. You might be familiar with Thomas Edison, who's credited with discovering, or kind of not discovering, but really inventing that first way of creating a light bulb using a filament. So different than these examples, different than our plasma globe or our spectrum tubes, instead of ionizing gases in order to produce light, filaments really rely on heat. So those kind of light bulbs are not very energy efficient, let's say. By putting electricity through the filament, you actually cause them to heat up so hot, almost like a combustion reaction, that they glow very bright. But you waste about 95% of the electrical energy that you put into an incandescent or filament-powered light bulb. So on the table here, I have a couple different examples of light bulbs that you might find either inside your house or at the hardware store. And some of these work better than others or are more energy efficient than others. So this is an incandescent bulb. It has a filament inside. You can see it right inside there. It's very, very small, very thin piece of metal draped between two electrodes. So when you power this up, we actually push power through that filament and it heats up very, very, very bright. But like we said, that's wasting about 95% of the electricity that we put through it. And those filaments, they really just don't last forever. So if you have incandescent light bulbs in your house, right, they don't last a very long time in comparison to our other options here. We'll get to those in just a minute. But this filament, right, has a lifespan. Because you're making it very, very hot, over time, the structure of that filament degrades. We saw something very similar during our kaboomistry episode. So I've got that experiment set up one more time. For this one, need some safety goggles here. I've got my fire extinguisher handy. And we're gonna do a burn using magnesium, which is a metal just like we might find in a light bulb filament. Not usually used in magnesium. And if you remember this segment, you might remember why. So if we burn our magnesium filament here, get it nice and hot. If it wants to light. we can see that that stuff burns extremely bright, but only for a very short period of time. Now our magnesium's gone out and there's really nothing left but a pile of ash. So these filament style light bulbs are wasteful of our materials since they kind of burn up, and of our electricity or the energy that we put into them. So that's an incandescent light bulb, something very similar to what Thomas Edison had invented. But next we have fluorescent light bulbs, and these light bulbs actually do use the same principle as our spectrum tube. This fluorescent light bulb is a vacuum tube. They can actually mold those glass tubes into shapes like this so that they fit inside our sockets. Just like our neon signs, we can actually bend glass. We then vacuum seal them and put electricity through them to ionize the gases inside. Where this light bulb, our incandescent, takes about 50 watts of power to light up, this fluorescent light bulb only takes about 12. So much, much less power needed to create the light from this light bulb, even though they'll burn at about the same brightness. Lastly, we have an LED. LED stands for light emitting diode, and this takes even less power. Because the electrical components inside are so small, they only require a very, very small amount of wattage in order to light up. So this will glow extremely bright, where this incandescent bulb used 50 watts. This LED will be the same brightness for about 4.5 watts. So less than 10% of the electrical energy for the LED compared to the incandescent. To show you how this might apply to your power usage at home, we've got something to share with you. This is an exhibit at the Michigan Science Center, and we have some different electrical devices hooked up to a power meter. So take a look around your house. You might have one of these power meters outside, but most of the time now they are digital. On these older versions of the power meter, we can actually see a disc spinning inside them to show us how much energy we're using. So the faster it spins, the more power you're using. The slower it spins, the less power you're using. So we've got two different kinds of light bulbs. We also have a radio and a blow dryer. So let's take a look at all four of these devices first and see just how much power they use. All right, so we've got our first light bulb here. That is an incandescent light bulb. And if you watch the little blue dots, they were moving along. Next, we have our radio. And you can see that we have very, very little movement of that disc. Now we've got a hair dryer, which is 1,875 watts, which is extremely powerful. Look at that meter go. And then very lastly, we've got a fluorescent light bulb. So powered by that ionization of gases. A little bit slower. So let's take a look at one more video. This one is going to focus on just the light bulb. So we'll take one more close look here at just the light bulbs. So first, our incandescent, which is powered by a filament, right? So we said that we have to put a lot of energy into that filament to cause it to light up. Look how much energy we're using on that meter. Look how fast those dots are spinning. That's a lot of power, right? Just for that one little light bulb. And you pay every month your electrical bill based on how many times that meter spins, basically. Next, let's take a look at our fluorescent light bulb. So this is not filament powered. This is powered by that ionization of gases. And watch the dots. They move much more slowly, right? Barely any movement at all compared to our other incandescent light bulb. And so we can see why changing out our light bulbs at home to these newer fluorescent bulbs, or even better, these LEDs, will save us money on our energy bill every month. So I've got one last experiment to show you. But before we do that, now is a great time to stop and see if you have any questions about our visible light spectrum, about the light bulbs that we've talked about so far. If you do have questions, go ahead and type those in the chat. I'll keep an eye on there to answer some of those for you. So type your questions in the chat. At this time, as always, we're going to take a moment to thank the sponsors of the Michigan Science Center. Our sponsors like Denso and the DTE Energy Foundation, they are funding the Michigan Science Center even while we're closed so that we can keep the science learning going for all of you at home. We're so excited that we can bring these programs to you on Facebook, on Zoom, on YouTube every weekday at 2:30 p.m. Remember that if you'd like to be alerted on Facebook when we go live every weekday, you'll need to like and follow the Michigan Science Center's Facebook page. So let's see if we have any questions coming up. I can see we've got a couple in the chat on Zoom. Someone would like to take another look at the dog vision picture. So let's go ahead and let's take a look at our dog vision here. All right, so here we have human vision on the left, dog vision on the right. So humans have great color vision. It's something that we've adapted over time, but that dogs just don't need as much as we do. And so their eyes, their receptors are different. They don't have as good of definition of color vision, at least. But like we said, they make up for that with their heightened other senses, like their extremely good hearing and their really, really good sense of smell. So we can see that in the human vision picture, right? We see red really well as humans, whereas dogs do not. And so everything that is in that red spectrum ends up looking kind of yellow to a dog. Let's see if we've got any other questions coming in. How does light move? That is a great question. To answer that, let's take one more look at our electromagnetic spectrum. So we had our electromagnetic spectrum that we talked about during the microwave episode, but we also showed it today. And we said that light travels in waves, right? It travels in these electromagnetic waves, meaning that there's one axis for electricity, the other axis for magnetism. But these waves are transverse waves. So if you remember our episode yesterday about sound, Raul told us that sound travels in waves, but those are compression waves, meaning that those waves look kind of like a slinky if we were able to see them, and they actually have to compress molecules in order to travel. So sound cannot travel through a vacuum like space. They have to have air molecules or solid molecules in order to propagate, but light, we know, does travel through space, right? Otherwise, we wouldn't be able to see the light from the sun. So light travels in transverse waves, which don't need a medium, whereas sound travels through compression waves. Great question. Someone asked, can you do the, so someone asked, is mercury a liquid metal? Yes. So if you heat up almost any metal, you can get it to be in its liquid form, right? Just by adding that kinetic energy. We warm up the molecules, they spread out, and they can turn into a liquid. Mercury exists as a liquid at room temperature, which is somewhat unique for metals in general. So that red stuff you see in a thermometer, that is liquid mercury. It's very red, but we saw that gaseous or ionized mercury is bright blue. Pretty interesting. How do we measure the speed of light? One of the easiest ways that we could talk about that is we know how long it takes for light to get to us from the sun. So we can track that by if something were to pass in front of the sun, right? We know how long it takes before that light gets to us. So there is a constant speed of light. It travels at a constant rate of, I think it's 3 times 10 to the 8 meters per second, which is extremely fast. But light travels at a constant rate. Someone asked, can we use the plasma globe? It is on here. Our plasma globe is on. We take a look over to the side at our plasma globe. It's kind of difficult to see with all the lights on here inside the studio, but if I put my hand on it, right, I'm a great conductor of electricity, and that ionized, electrically charged gas inside is attracted to my hand because I'm a much better conductor than the air around the globe. And so all of it gets kind of focused onto my hand, and we can see those lightning bolts or the plasma bolts inside the globe. Great questions. Someone asked, how do LED lights save energy? And it's just about the amount of power they take in order to light up. So we said that this just, since all the components are so small, these diodes only take about, for this light bulb at least, the packaging told me that this only takes 4.5 watts of power. So that's not very much, especially we said that our incandescent bulb took 50 watts, so less than 10%. So if we were to compare these two on the power meter, our incandescent bulb would turn the meter very, very quickly, and the LED would turn our meter very, very slowly, almost unnoticeably. All right, so we do have one last experiment that I'm really excited to show you. If you do still have questions, keep typing those in the chat. We might have time for one or two more after our last demonstration here. This one is actually a light bulb that I've created myself using the same principles that Thomas Edison had come up with. So to power our light bulbs, instead of plugging this into an outlet, I've actually taped together 8 D-cell batteries. So I've got 8 D-cell batteries here. Each one gives us about 1.5 volts of power. Linked together like this, by the end of it, we do lose a little bit, and it gives us about 13.5 volts at the end. And then it gives us about 6 amps of power, which is quite a bit. So we're actually going to use that as our power source. And then I've set up a couple other materials here. So we said this is similar to an Edison light bulb or an incandescent light bulb. So you can see that I've set up a filament here. This filament is made out of pencil lead. So the same lead that you would find in a mechanical pencil. I've got some of these refills here. I've just very, very carefully clipped one of those lead refills between 2 alligator clips. Since this is going to be a light bulb, right, we want to trap our light inside something. So I'm going to slide our mason jar very carefully right over the top, being sure that I don't put too much pressure on anything so we don't snap our filament before it lights up. Right, we know that incandescent light bulbs are very delicate. So if you drop them, you can actually break that filament. It needs to be completely intact in order to have the electricity travel through it and in order to light up. So all of this being said, it's very, very delicate. And now all we need to do, right, is power up our light bulb. So we've got our one end of our electrode here, other end of our electrode here, and we're just going to tap the sides of our battery strip here. And let's watch what happens to our filament. Maybe let's zoom in just a tiny bit more. There we go. And let's go ahead and power up our light bulb. All right, let's make sure I didn't break my filament here. Let me double check just to make sure we still have good contact, that I didn't break anything. Like we said, they're very, very delicate. Worst case, I might just need to change out my filament here for one that may not be broken. Let's go ahead and see. These are the times where I wish I had a video of it working right before our segment started today. Let me see, last idea I have is let's try to switch our power. It shouldn't make a difference since we don't have a directional current going through our filament here. We're really just trying to use our electricity. Maybe if I push my battery stack all together, make sure we have good contact here. There it goes. And our filament is glowing really, really brightly. We're kind of filling our jar full of smoke here. As the integrity of that filament is lessened over time, it's glowing really, really bright, right? And so we've actually made a light bulb the same way that Thomas Edison had. But you can see that pencil lead, maybe not the best filament we could have chosen, right? If we take off our jar here, we can see that it's actually broken. So the heat eventually became too much for this tiny little piece of pencil lead to handle. It did break in half. And so we can see why these light bulbs are not only inefficient, but they're also extremely delicate. So that's about all the time we have today. Let me see if we have any very final questions. Can we get electricity from light? The answer is yes, right? So if you've heard of solar power, we can actually harness electromagnetic rays with solar panels and turn them back into electricity that we use in our homes. Great question. So we can get power from all sorts of sources, right? And all of those power sources are the power that we use to supply the devices inside our home. So thank you everyone so much for joining us. Keep sending your questions in the chat. We will get around to answering those. If we have any pressing questions, we can always do another Echo Live on light. And we will see you all next time. So thank you so much for joining, and we hope we'll see you back here tomorrow for our last Echo Live program of the week. And I promise I won't be wearing my pajamas tomorrow, but we'll see what the holiday might be. Bye, everyone. Thanks for joining.